Differentiability. So I'm going to start off with the function tree that I've given you. So if you have a function and you're looking at the function at a specific point, so I'll even put A right here. A function can either be continuous or the function can be not continuous at that point. And if it's not continuous, you have four ways to be not continuous. You can have a removable discontinuity. That's when a factor simplifies. You can have an infinite discontinuity. That's when the factor in the denominator does not simplify, gives you undefined, gives you a vertical asymptote, which is the same as an infinite discontinuity. A jump discontinuity is most common with piecewise functions with the greatest integer function. And then oscillating, which I really wouldn't worry too much about, but understanding that there are a total of 4, that's the sine of 1 over x. If the function is not continuous, that's the easy one. It's 100% not differentiable. So f prime of a will not exist if that a value is any of the not continuous points. Now the harder thing is if it's continuous. You could have two things happen. It could be differentiable, which means that f prime of a exists, meaning it could be 0 or any other value, but it won't be undefined. Or if it's continuous, it could be not differentiable. Which means that f prime of a does not exist. And there are 3 of those points. So actually, let me move this down. So I have a little room. Alright, 3 points. One is a corner. How do you get corners? Either piecewise or with the absolute value functions. Second is a cusp. A cusp happens very easily when the power of x is less than 1 but greater than 0, and the value is a fraction where the top numerator is even and the denominator is odd. So x to the 2/3. The third example would be a vertical tangent. And a vertical tangent similar to the one above. A vertical tangent occurs when you have a power of x between 0 and 1, but that power is odd over odd. So 1/3, 1/5, 3/11. Those would all create a vertical tangent. Now, for each of those, you should be able to tell me what the definition of the derivative is. So a corner, I'm only going to do it for, let's not do a corner. Let's do the more difficult one. So let's look at a cusp. That's an example of a cusp, and so is this. And what you'll notice is the derivative as you come in from the, left side is negative, but after you pass the cusp, the right side is positive. So the derivative coming in from the left for a cusp will be positive or negative infinity. I'm actually going to write it with an over. But then the limit as h goes to 0 from the right will actually be the other infinity. So if this is positive infinity, then this one has to be negative infinity. If this was negative infinity, then this one has to be positive. The difference between that and a vertical tangent. So a vertical tangent, if you look at this graph, the slope is positive here, positive here, it actually stays positive. So the difference would be that if this one was positive infinity, then this one would also be positive infinity. That's what makes the difference between a vertical tangent and a cusp. So now you're going to have a problem to do. I want you to identify where the points of discontinuity occur. Not points of discontinuity, points of non-different, I'm tired. Non-differentiable points, wherever the derivative doesn't exist. Alright, so go ahead and press pause now, try the problem, and then you can check your answer. Alright, so I can identify that that piece right there is an even over odd with a power between 0 and 1. So I know that that's going to give me a cusp. Where the cusp occurs, I'm going to look at who owns that power. So that power is this guy's power. Therefore, you take the inside of the power and set it equal to 0. I get 2 cosine of x equals negative 1. Cosine of x equals negative 1/2. Negative cosines happen in second and third quadrant. So x is equal to, my second quadrant answer is pi over 6. 2 pi over 3. And then the fourth quadrant answer is 4 pi over 3. Third quadrant answer. And then, because I didn't give you a restriction, it means that you have to give me all the answers. So this one is the second quadrant answer, 2 pi over 3. And every angle that is one revolution around from there would also count as an answer. So one revolution would be 2 pi. And the way that we say revolutions, 4 revolutions would be if we like k, and we then say that k has to be an integer. So you can't do half a k. What that means is half a k would lead us into the fourth quadrant. You need a full k all the way around. So we can do the same thing down here. And then this is a symbol for integers. And this is what I'm going to write in subset notation.